Hi, I'm Antonin, and together with Romain and Quentin, we are going to present to you our robot that will participate in the Robotic French Cup. The Robotic French Cup is one of the largest robotics competition in France. It takes place over 3 days in La Roche-sur-Yon, where teams from all over the country compete in 5 matches before the top 16 advance to the final phase. The challenge: our robot must navigate the area, manipulate game elements, cans and planks, to stack them and create platforms. It's an exciting competition that pushes our technical and strategic skills to the limit. I'm personally in charge of the mechanical design. This is an ongoing process because it constantly adapts to changes and isn't really final until the day of the competition. The mechanical structure needs to be both precise and reliable to support the robot's functions. Our design process starts in Onshape, where we model every component in 3D before manufacturing them. This allows us to realize how parts fit together and optimize them before production. The chassis of our robot is made of wood, which we cut using a laser cutter. This method ensures high precision while keeping the structure lightweight. Wood is a great choice because it's easy to work with and provides enough strength for our design. Most of the mechanical parts of our robot are 3D printed in plastic. This technology allows us to quickly prototype, test, and iterate. On average, each part requires 2 or 3 iterations to be fully functional, sometimes even more. Each piece must fit within the limited perimeter of the robot, so we need to carefully optimize the size and positioning. Every millimeter counts. The key mechanical components of our robot are the actuators, which allows us to pick up and move cans and planks. These actuators use servo motors for precise control. The goal is to stack the planes on top of each other, creating stable platforms to score points. The mechanical structure is essential because it supports all other aspects of the robot: electronics, programming, and strategy. Without a strong and efficient mechanical design, nothing else would work properly. Now that we've covered the mechanical side, let's move on to the electronics. Romain will explain how we control and power the robot.
When we think about how robots move, it's useful to compare them to the human body. Just like us, they need muscles, a control system, and a way to distribute energy efficiently. First, let's talk about servos. These are like small actuators responsible for the precise movements. If you imagine a robotic hand, each finger's movement is controlled by a servo, just like our muscles contract to move our fingers. But servos don't work on their own. They receive commands from microcontrollers, which act as the robot's brain, telling each servo how much to move and when. This is what allows robots to perform delicate controlled actions. While servos handle fine movements, motors take care of the more demanding tasks. Think of them as big muscles, the one responsible for lifting, rotating, or moving large parts. If servos are like the small muscles of your fingers, motors are like your legs carrying your body weight when you walk or jump. Motors provide raw strength, whether it's powering the wheels of a robot or the arm of an industrial machine. So far, we have been thinking at the human scale: muscles, movement, coordination. But let's scale up. Instead of thinking of a single person, imagine an entire city at work. In these energies, servos are like people moving around and handling specific tasks. Motors are like vehicles and heavy machines responsible for transportation and large-scale movement. Processors are like city infrastructures, control centers, offices, and communication networks, organizing everything. But just like a city, all of this needs power. A robot's battery is like a massive water reservoir holding stored energy. But just like a city can't be flooded with water all at once, the robot can't send all of its battery power everywhere at the same time. That's where the power board comes in. It acts like a dam, regulating energy flows to different areas. Some places require more power, like industrial zones with factories, motors. Some places need steady controlled energies, like offices and homes, servers and processors. If there is too much energy in one place, it's like a flood hitting the city, overwhelming and damaging infrastructures. If there is not enough, parts of the city thirst for water, just like a robot shutting down because it isn't getting enough power. The power board ensures each part gets exactly what it needs, keeping the robot running smoothly, just like a well-managed city. For the robot to operate without human intervention, it must be fully autonomous, making its own decisions. This is accomplished through algorithms which guide the robot's actions based on its environment and goals.